lesson, we're going to learn about the MOS transistor and ultimately derive a small signal model for the MOS device. To begin with, we'll look at the Mos Cross Section. The MOS device is typically built from a single substrate, and in most modern commercial CMOS processes, the process begins by laying down a P- silicon substrate. Into this P- silicon substrate, we add a couple of implants. The first implant will be an N+ contact. These will comprise the source and drain contacts. And a P+ region is added to make contact to the substrate, to make an ohmic contact to the substrate. Between the source and drain contacts, an oxide layer is grown. And above this oxide layer is a gate material, which can be polysilicon or polycrystalline silicon, or in more modern processes is actually some hybrid metal, and they use a different insulator. But the structure is roughly the same. There's some insulator separating a metal or metallic contact from the bulk silicon. So here we have our gate, and either of the N+ regions can be the drain or the source. We'll learn that unlike BJT, the drain and the source can be interchangeable and typically are defined simply by the voltage potential that they're hooked up to. A Pmos transistor, so this is an NMOS device. A Pmos device looks almost the same, except that in a CMOS process we would start with a P- material. We would implant an N+ region, and in this implanted N+ region we would implant P+ channel. We'd separate the channel with an oxide layer, and finally with our gate material, which would be our polysilicon or conductor of some sort. So this would be our gate, this would be our drain or source, and this other terminal here would be our other drain or source. Now, looking at the symbols for our transistors, we have NMOS symbols can look as follows. We can either use a symbol that has an arrow, at the source. Our Pmos transistor will have an arrow at the source as well, but it will be going in the opposite direction. And our bulk contact has an arrow coming out of the terminal. Or, for logic, oftentimes, because again the source and drain can be interchangeable, they don't mark the source or the drain, and they just use a generic symbol like so, or we put a bubble at the gate of the Pmos device to let us know that it's Pmos instead of NMOS. Now, in the NMOS device, the current is always flowing from the drain to the source, and we don't have a gate current, or we have a minimal gate current because the gate is separated from the silicon material by an insulating layer. So ideally no DC current flows. Now in our Pmos device, the current just flows in the opposite direction. So our current would flow from our source to our drain. And this just has to do with the majority carrier that's being used. Similar to the bipolar transistor, we have a couple of different regions of operation for the Pmos device. So if we look at a couple of characteristic curves for the Pmos device, they're going to look very similar to those that we saw for the bipolar transistor. So if we look at a curve that is the drain current, ID, versus the drain to source voltage, we would see a set of curves like so, where each of these curves would represent different VGSs. So we have three primary modes of operation for the Mos device. The first mode would be cutoff, and that would be where zero current flows. Like in the bipolar case, we have a line that demarcates the separation between what we call the triode or linear region and what we call saturation. In a Mos device, saturation is good, and a bipolar device, saturation is bad. Unlike in a bipolar device where the saturation region is useless, or nearly useless, we use the triode or linear region in a Mos device as a linear resistor. We can also look at a characteristic curve for current versus gate to source voltage, VGS, and this would look like so. There would be zero current until a point where we reach the threshold voltage, and then the current will increase proportionally to the square of the gate to source voltage less the threshold voltage. We'll come back to these curves in a moment to find the small signal model parameters. But in the next part of the lesson, we'll learn about the regions of operation and what voltages define those regions of operation and what's happening physically inside the device in those regions of operation.